All right, hello. We're going to start our section on Chapter 6, looking at motion in 2 dimensions. And today we're going to look at Section 6.1, which involves projectile motion. So projectile motion talks about objects going through the air, and all objects move through the air in a parabola shape. So if you remember from math, parabola comes up, curves, and comes back down, and the idea being that this shape is symmetrical, or the same on both sides. And we can use that principle when we talk about problems involving projectile motion. So the projectile is the object that's shot through the air, whether you're tossing a football or tossing a tennis ball up in the air or throwing a piece of paper into the trash can. Those are all considered projectiles. After giving a projectile its initial thrust, so when you throw that piece of paper in the trash can, after it leaves your hand, the only force acting on this object is gravity, and that's going to become really important as we start talking about these problems. Gravity causes the downward shape, or the downward curve in the parabola. So we give an object an initial velocity in the upward direction. As soon as that object leaves our hand, gravity is acting against it. And so eventually what will happen is by the time the object gets to the top of its path of motion, velocity will have come to 0, but because gravity is still acting on the object, we still have an acceleration, which means the velocity is still changing. Once it's reached the top of its path of motion, now velocity will start to increase because now gravity is acting in the downward direction. So let's talk about trajectory. Trajectory is the projectile's path through space, so that parabola shape. And if we know the initial force, then we can find the trajectory. And some things that we can find with trajectory involve range and maximum height. So if we have our parabola shape, our range is how far horizontally the object is going to travel, and our maximum height is the maximum vertical that the object is going to travel. So from the top of the object's path of motion to the ground. Well, we've talked about 2 different directions of motion, horizontal and vertical. And just like in Chapter 5, where we took vertical and horizontal forces and broke them apart, we have to do the same thing with motion. And so when we do projectile motion, this is a combination of horizontal and vertical together. And so we need to separate them out. So we separate the horizontal from the vertical, and they don't affect each other. The horizontal motion of the launched object does not affect its vertical motion. And so this is seen when we either drop or throw an object. If you take a look at this photo or this picture down here, we've got an object that is being thrown, I'm assuming down, or just dropped from the air. Okay, and we have looked at problems like this, where we assume they're just in free fall, and we're dropping them from a certain height. And you can see that over time, the distance that the object has traveled within, maybe each of these is a second, has increased. And that's due to the fact that gravity, the acceleration due to gravity, is causing the object to speed up and cover more distance in the same amount of time. If we throw a ball from that same height, okay, you can see that vertically, they are lined up. And so vertically, they are traveling the same amount of distance. Now, horizontally is a different issue, right? Because when we throw an object, we are giving it a vertical and a horizontal force. Okay? Whereas when we drop an object, we're just giving it vertical. But that horizontal component is completely separate from the vertical and will not affect the vertical path of motion. So the vertical positions are the same, and the vertical motion, or that downward velocity, is due to gravity. So the motion of a projectile is the vertical and horizontal put together, but we have to keep them separate when we're doing problems with this because we can't add vertical and horizontal vectors together just by adding them. So for the horizontal path of motion, we're going to say that this part is constant. We're not giving it a horizontal force. We're giving it an initial horizontal velocity, but after that point, nothing else horizontally is acting on it. We're going to assume that there's no air resistance. And so what that means is that the horizontal vectors are going to be constant throughout the object's path of motion because there's no force horizontally, and in order to have a change in motion, we need a force. And so this would be considered constant velocity. We're going to assume no air resistance. For vertical, you can see that first off, we give it this vertical motion in the upward direction. Gravity is acting against it, so you can see our arrows getting smaller through time until we get to the top of the object's path of motion. At the top, velocity will become 0, but because there's still vertical acceleration, we will keep changing the velocity and then start our downward path of motion. Now you can see the velocity vectors in the vertical direction getting larger because now gravity is acting in the direction that the object is traveling. You can also see that the point of our vertical vector here is identical to the point of our vertical vector over here, and we're going to get into that in a minute. So when you are solving problems involving projectile motion, the first thing you need to do is divide your motion into horizontal and vertical vectors. For the vertical motion, because the only thing acting on it is gravity, we're going to assume that it is in free fall. And so that involves the formula d final equals d initial plus v initial t plus 1/2 at squared. And we have used this equation in the past to solve free fall problems. For horizontal motion, because after that initial velocity we're assuming no air resistance, that means that horizontally the velocity is constant. If we find the horizontal velocity at the beginning, then that stays the same throughout the object's path of motion. And that's a really key thing to remember, that horizontal velocity is constant. Because time is going to be the same for both directions, vertical and horizontal, if we solve for time in one of the directions, it's going to be the same for the other direction. And so we can use time to kind of link horizontal and vertical motion to each other. So here are some practice problems. You can try them on your own, but we will also do them in class. Okay, and anytime you're launching a projectile, we're launching it at a specific angle. And so we've already looked at how the different angle affects things like height and range. Okay, but because projectiles travel in a parabola shape, the path of a projectile is symmetrical. And so if we look at that parabola, and we've got this symmetrical shape that we can split down the middle. So at each point in the vertical direction, the velocity up and down are the same. It's just that the downward is negative, because we usually indicate negative direction as being downward. So at this point in time, I could find the vertical velocity, and it would be identical to the velocity at this point. This one would just be negative because of the direction that it's traveling. So there are two main parts to the path of motion for a projectile. The first one is the highest point. Okay, so at this point, vertical velocity is 0, and we just have horizontal velocity, because we know at the top of an object's path of motion, velocity in the vertical direction can become 0 for a second. But we know that horizontal velocity is constant throughout the path of motion. The second part of the path of motion is the range. This is the horizontal distance an object travels. And so from start to end, this is your range or horizontal distance. So we were trying to solve for this value, we would need to use horizontal velocity, not vertical. Well, trajectories also depend upon the viewer. If you're tossing an object on a moving bus, that's going to be a little bit different than someone standing still on the sidewalk. Although your projectile is going to behave the same whether you're on the bus or on the sidewalk, what this involves is what's called relative velocity, which we'll talk about a little bit more in section 3. Because the bus is moving and you're also tossing the object, it can look different than if you're standing still on a sidewalk. Air resistance is important, and up till now we've kind of ignored it, and it can affect objects in a big way. So for example, a golf ball will have dimples on it to reduce the effect of air resistance and allow it to travel further. Baseballs and softballs are the same way as far as the threads on them. You would hold a baseball or a softball in different ways to get different styles of pitching, and that's due to the threads and air resistance and how it's going to travel across the plate. So here are some additional practice problems. Feel free to try these, or we'll go over them in class. And then here's the homework. Have a good day.